Good day everyone, and welcome to our presentation. Today, we delve into the fascinating world of scientific knowledge absorption through language models, as we discuss our paper, Galactica, a large language model for science. We'll explore how Galactica, our proposed model, disrupts the traditional store and retrieve paradigm, absorbing vast amounts of scientific knowledge and outperforming existing methods. Stay tuned as we unravel the potential of language models in transforming how we interact with knowledge. Thank you. The traditional approach of storing and retrieving scientific knowledge has its limitations. It heavily relies on human effort, creating a bottleneck in knowledge throughput. Existing methods, such as search engines and databases, present their own set of challenges. The bottleneck for language models, on the other hand, is the availability of high-quality, step-by-step datasets. Additionally, the quality of text extracted from sources like Common Crawl needs improvement. Now, let's talk about our proposed method. We suggest using language models, specifically Galactica, for accessing and interacting with scientific knowledge. Galactica has shown promising results in absorbing technical knowledge and performing tasks like citation prediction and knowledge-intensive question answering. This approach could potentially disrupt the traditional paradigm and pave the way for a new interface for humanity to interact with knowledge. Let's take a look at this illustration of human working memory. It's a complex system, isn't it? Now imagine trying to access scientific knowledge using the traditional store and retrieve paradigm. It's a method that has served us for over half a century, but it has its limitations. The most significant of these is the heavy reliance on human effort to reason, combine, and organize information. This leads to what we call a knowledge throughput bottleneck. In other words, the speed at which we can process and understand new information is limited by our human capabilities. This is the problem we're trying to solve. Language models hold immense potential to disrupt the traditional paradigm of accessing scientific knowledge. They can provide a new interface for knowledge interaction, going beyond the limitations of search engines and databases, which often struggle with reasoning and organizing information. However, the full potential of language models is yet to be realized, largely due to the bottleneck of availability of high-quality datasets. Our work proposes a novel use of language models to absorb technical knowledge, such as LaTeX equations and chemical reactions. We've used Galactica, a language model trained on diverse sources, to demonstrate this. This approach opens up new possibilities for how we interact with and utilize scientific knowledge. The quality of text extracted from Common Crawl is generally poor, necessitating the application of stringent filters. This is an important area for future exploration, as improving this could help us capture more base scientific knowledge. Now, let's consider a key question in language model training. When incorporating new scientific knowledge, should we start from scratch or build upon older checkpoints? This remains an open question, and further research is needed to determine the most effective approach. We propose a novel approach to accessing scientific knowledge, one that disrupts the traditional store and retrieve paradigm. This new method addresses the significant bottleneck in knowledge throughput that we currently face. Our methodology hinges on the absorption of technical knowledge by language models. These models are capable of understanding complex LaTeX equations and chemical reactions, demonstrating their potential in scientific fields. We've trained our model, Galactica, on a diverse range of sources, including Wikipedia and Common Crawl, to ensure a broad and comprehensive understanding of various topics. This approach opens up exciting possibilities for the future of scientific research and knowledge discovery. Our research has delved into the training process and performance of language models, specifically using a working memory token approach. This approach has shown strong performance on mathematical benchmarks such as MMLU and math. In terms of experiment design and evaluation, we've tackled a variety of tasks. These include citation prediction, knowledge-intensive question answering, IUPAC naming, and even drug discovery. The power of language models lies in their context, associative abilities, which we've leveraged to great effect in our experiments. This approach has the potential to revolutionize how we access and process scientific knowledge, moving away from the traditional store and retrieve paradigm and towards a more dynamic, interactive model. Our research has unveiled the immense potential of language models. They can serve as powerful tools for exploring literature and scientific knowledge, absorbing technical information like LaTeX equations and chemical reactions with surprising ease. This ability to compose a curated knowledge base is a significant step forward. Moreover, we found that language models can act as a bridge between scientific modalities and natural language. For instance, tasks like IUPAC naming, which are traditionally complex, can be learned through self-supervision. This opens up exciting possibilities for tasks like automatic protein annotation, further expanding the scope of language models in scientific research. Let's delve into the technical results of our study. The figure on your right showcases Galactica's attention to functional groups in the IUPAC naming task. This is a testament to its ability to absorb and apply technical knowledge. In terms of key results, Galactica has outperformed traditional methods in citation prediction, demonstrating its prowess in understanding and predicting academic trends. Furthermore, it has achieved high performance in knowledge-intensive question-answering tasks, highlighting its potential as a tool for scientific inquiry. These results underline Galactica's capacity to not only understand complex scientific concepts, but also to apply this knowledge in a meaningful and practical way. Galactica has shown impressive capabilities in absorbing and utilizing technical knowledge. It can effectively handle complex elements such as LaTeX equations and chemical reactions, demonstrating its potential in scientific and technical domains. In the realm of citation prediction, Galactica has surpassed Tune's sparse and dense retrieval pipelines. This indicates that it offers a more efficient method for predicting citations, a crucial aspect in academic research. Lastly, Galactica has demonstrated strong performance on knowledge-intensive tasks. It has performed well on mathematical benchmarks, such as MMLU and math, showcasing its potential in solving complex tasks. This suggests that Galactica could be a powerful tool for tackling intricate problems in various scientific fields. Diving into the technical results, we find intriguing implications from our ablation studies. Galactica's performance suggests a potential disruption of traditional knowledge access methods. It's not just about storing and retrieving information anymore, but about understanding and predicting it. We've seen efficiency and accuracy in citation prediction using language models. Galactica's success in this area points to a more efficient and accurate method for citation prediction, which could revolutionize how we approach this task. We also see the potential to alleviate the knowledge throughput bottleneck with language models. This could open up new avenues for information processing and dissemination. However, we must also acknowledge the need for high-quality, step-by-step datasets. This is a crucial component in ensuring the effectiveness of our models. In summary, Galactica's strong performance implies a potential shift from the traditional store and retrieve paradigm. It's about more than just storing information. It's about understanding and predicting it. This disruption of the traditional paradigm could have far-reaching implications for how we access and use knowledge. Let's delve into the technical results of our research. A key achievement is the alleviation of the knowledge bottleneck. With language models like Galactica, we can potentially reduce the reliance on human effort in complex tasks. This is a significant stride forward, as it opens up new possibilities for automating and streamlining processes in various fields. The implications of this are far-reaching, and we're excited to explore them further in our future work. As we draw conclusions, let's reflect on the transformative approach Galactica brings to accessing scientific knowledge. We're moving away from the traditional store and retrieve paradigm, and instead, we're harnessing the power of language models. The figure here illustrates Galactica's impressive performance in citation prediction tasks. As the model scales, its citation distribution closely mirrors the ground truth, underscoring its superior predictive capabilities. This shift in approach, leveraging models like Galactica, is not just a change, but a leap forward in how we interact with and understand scientific knowledge. Language models have shown remarkable potential as absorbers of technical knowledge, with their performance scaling smoothly as the model size increases. They have demonstrated advantages over traditional search engines, particularly in citation prediction and knowledge-intensive question-answering tasks. Our research also highlights the potential of language models to bridge the gap between scientific modalities and natural language. We've seen promising results in tasks such as IUPAC naming and drug discovery. However, there are still challenges to overcome. The availability of high-quality, step-by-step datasets is a current bottleneck. Additionally, the quality of text extracted from Common Crawl is often poor, which presents another area for improvement. In conclusion, while there are hurdles to overcome, the potential of language models in the realm of scientific knowledge absorption is undeniable and exciting. Language models, as we've seen, hold immense potential. They're capable of absorbing technical knowledge and can potentially take on tasks that are currently human specialisms. We are excited to see how the open machine learning community will further advance these models. Looking ahead, there are important questions that need to be addressed. One of them is whether we should retrain models from scratch or from older checkpoints to incorporate new scientific knowledge. Another critical aspect is ensuring the correctness and factualness of the generations of these language models. These are areas that require further research, and we look forward to the insights that future studies will bring.